we are doing SQL, which is a commercial language with which combines both relational algebra and relational calculus, and we saw that the structure of any SQL query is of the type select a set of attributes from a set of relations where P is a predicate, and this is equivalent to the Cartesian product of the relations, a selection out using the predicate P and a projection of the attributes A1 to AN. We have seen several simple examples of these, and among them we saw how to select out attributes, how to do a natural join, and how to use rename variables so that we can do a natural join or combine the same relation using different names. We shall continue with those examples, and we shall bring back the example which we were doing last. The example was select T dot accession number T dot S name from sub T sub S, where T dot price is greater than S dot price and S dot S name is equal to Narosa. The sub relation has got the attributes accession number, price, date of issue, supplier name, and date of, sorry, the sub relation has got accession number, the supplier name, price, and date of supply. It gives out the name of supplier who supplied this accession, the book with this accession number at this price and at this date. And this query, which we saw, finds out the name and accession number of the books and the supplier who has supplied the book of all those books, such that the price of that book is greater than the price of any one book supplied by Narosa, which is, since this is greater than and it is any one book supplied by Narosa, it is equivalent to saying that this is greater than the price of the least cost book supplied by Narosa. Now, this greater than can be replaced by other things as well. This may be greater than equal to, then it will be greater than equal to the least cost price. Okay, it may be equal to. Suppose this was equal to, then we would have got, give me the supplier name and accession number of those suppliers who have supplied a book which is equal to the price of some book which has been supplied by Narosa, any one book. If it is equal to any one book supplied by Narosa, then I will be able to get it. So, greater than, equal to, even not equal to is there. Now, this may be written out in a different format in the computer language, you can maybe cannot write out this symbol, but the not equal to expression is also there. So, you may get out the accession number and book such that the price is not equal to any one book, because we are doing a Cartesian product. Now, SQL provides you a more natural way to write out this query. So, we will first start with this and then we will see how. Since this is related to some book, see, price of this book must be greater than some book supplied by Narosa. So, SQL provides you a statement using this. The query is like this. This is the same query as the previous one, but it is more logical in the sense it is easier to understand this query directly and therefore to write it as well. Underlined are the keywords. These are SQL keywords. Select accession number S name from supplier where price is greater than sum. Now, from this set, this element is greater than some element in this set. These two together say that this is greater than some element in this set. Now, what is this set? This is the set of prices of books supplied by Narosa. This is the set of prices of books supplied by Narosa. Select price from sub where S name is equal to Narosa. And I want the accession number and S name of sub. Now this S name is related to this sub, and this S name is related to this sub. I want the accession number and S name of the supplier from the sub relation such that the price is greater than some element here, which is equivalent to the previous query which we had, namely this. Accession number S name sub ST, price is greater than S price, and S name is equal to Narosa. This is a direct relational algebra expression. SQL provides you a slightly better format to write out this expression. Now here we may replace this one by greater than equal to, not equal to, etc., and get the same answer. And more interestingly, we may replace this sum by all. If we replace this sum by all, then we have select accession number and S name from sub such that the price is greater than all of this. If the price is greater than all of select price from sub where S name is equal to Narosa, then we have been able to get out the supply name and accession number of those books which are more expensive than all the books supplied by Narosa, the greatest book supplied by Narosa. All right. You can have greater than equal to, you can have less than equal to, you can have equal to, you can have not equal to here as well, and this can be replaced by sum and all. So in set we have got the in, we have got the sum, the all. These are the operations we have on sets. That is, element is in this set, element is greater than all, element is less than all, element is greater than some, less than some, like that. Between two sets we have the union and intersection operation, and now we shall see we have got the subset operation as well provided by SQL, and that is using the contains keyword. To get the largest price in Narosa. You want to get the largest price in Narosa. The question is, how do I get the largest price in Narosa? Okay. Can we use this? Definitely we can. Let us see how we will do that. How we will get the price of the largest book supplied by Narosa. Select price from sub where S name equal to Narosa and price greater than equal to all. Select price from sub. I am using this query directly, the style directly, where let us see what we have done. This part is the same as the original one. Select price from sub where S name is Narosa. This gives you the set of all prices of books supplied by Narosa. And now from here I want to select price from sub where S name is Narosa. This price and this is related to this fellow. And this price is greater than equal to all of this. So the price of Narosa, which is the maximum, will be the only one which is greater than equal to all of this. So that price you will get out here.
Sub D, then compare that.
If you do sub S and sub D and compare, suppose we do it in the traditional way. Suppose we try to do it in select what? T dot price? Is that you want?
Select S name from select S name.
S name. But we want the largest price.
Yeah, sorry, select price.
Select price from sub
Yes.
S, comma
Sub
sub T. So here it will be T dot price or S dot price.
Sub dot S dot price.
Okay, let this be S dot price.
Where
Where
S dot price
S dot price
greater than T dot.
greater than T dot price. Very interesting. Let us see. Does this give us the maximum price of Narosa? This definitely gives us the maximum price of Narosa. This we are sure. The price of the largest, highest supplied, the book which has got the largest price supplied by Narosa. And here, obviously, what do you want?
S name equal to S name equal to Narosa.
No, S dot S name equal to Narosa and T dot S name equal to Narosa, isn't it? Now let us see what this query means. We are trying to select out the largest price of Narosa. S dot price from S and T such that S dot price is greater than T dot price in Narosa. So we are going to check columns where in the Cartesian product both are Narosa. That is fine. Now, and S dot price is greater than T dot price. Now, suppose Narosa has supplied two books. One is of price 20 rupees, another is of price 30 rupees. Then we will get the 30 rupees out here. Suppose Narosa has supplied three books. One of 10 rupees, 20 rupees and 30 rupees. So in one column this 20 rupees will be greater than the 10 rupees and that will also come. Okay. So this will not give you the query. I'll tell you what will give you the query. If you want to do it,
prices which is more than the list price.
wait, I'll tell you what will give you the query. Select price from sub. If you want pure relational algebra style, what does this give you? The set of all prices by Narosa. And what does this give you? What does this give you? No, no. This one will give you except the smallest. Okay? This one will give you all prices except the smallest. This one will give you all prices except the largest. You do this minus this. You will get it. This is pure relational algebra style. This, if this is A and this is B and this is less than, then this will give you all which is except the largest price. So A minus B will give you the answer of the largest price. This is pure relational algebra style. Alright. So if you write down here greater than, you will get everything except the smallest. And if you write less than, you will get everything except the largest. This is what I wanted to stress in both the cases. So now you are aware that if you want to write it out in pure relational algebra style largest, it will be slightly complex. And SQL provides you a much neater mechanism for it is logically more comprehensive to understand. That's all. Now let us see another interesting query which has the contains operation. The contains is the subset operation. A contains B means A is a subset, A is a superset of B. A contains B, that means B is inside A. So superset. So let us see this query. Select T dot S name from sub T, where the whole thing is inside the where. Select title from book where T dot accession number is equal to S dot accession number contains select title from book user borrow where book dot accession number equal to borrow and user dot card number equal to borrow dot card number and user dot b name equal to Vijay. The query is a big one, but we will break it up into few parts, and once we break it up into a few parts we will be able to understand it. Let us see this inside part. First, select title from book user borrow. So let us go back to our original database. Book accession number, year of publication, title, user card number, name, address, borrow accession number, card number, date of issue. So the common attribute between book and borrow is accession number, and user and borrow is card number. And here select title from book user borrow, where you did a natural join between book and borrow and a natural join between borrow and user. So it's actually a natural join between book, user and borrow. I hope this is clear, that it is a natural join between book, user and borrow, where user is Vijay and you took out title. So this gives you the title of all the books borrowed by Vijay. This part gives you the set which is the title of all the books borrowed by Vijay. Is that okay? So title of all the books borrowed by Vijay is available here. This also, this part, the part which is slightly above it, this part, select title from book S where T dot accession number is equal to S dot accession number. Actually we are using ideas of tuple relational calculus here. We want that T in tuple relational calculus where this T dot accession number is equal to the S dot accession number. That is, I want T such that there exists a title whose accession number is equal. So this will select out all possible titles of all books, which is supplied by a particular supplier, any supplier. Take any particular supplier, that supplier must have supplied this book. Okay? This part, suppose in my answer, let us understand it from the tuple relational calculus point of view. Suppose in my answer I have got Narosa. This gives me Narosa. Narosa allied and 3-4 things it gives me. Then for Narosa, this part will give me the title of all the books which is supplied by Narosa. This part will give me the title of all the books supplied by Narosa. If Narosa is there in my answer, because I have said select T dot S name from sub T, where select title from book where T dot accession number equal to S dot accession. So this part will give me the set of all books supplied by Narosa. Let us try to understand it in a factored manner. Let us see what this part of the query means. Suppose this is my full query. Suppose this is my complete query. Let this be my complete query. This can syntactically this is a complete query. Select t dot s name from sub t, where select title from book s, where t dot accession number equal to s dot accession number. Now this cannot be directly. This is not directly looking like a relational algebra expression. But as I said, that SQL combines both relational algebra and relational calculus. This looks like a relational calculus expression. What do I have? I want those tuples such that there exists S element of sub T dot S name and there exists B element of book such that S dot accession number is equal to B dot accession number. I want to select out, I want that tuple, I want only the name. That name must belong to some supplier, and that supplier must have supplied a book, and there must exist a tuple in book such that these two are equal. This is the meaning of this query. This part means this. So it will return true. Where needs a predicate? I agree, because this contains this. This does not return a predicate. I agree. See, this is not, it has been pointed out that this is not in pure SQL syntax, because where this needs a title. But what I wanted to point out is this part. This part of the query is equivalent to this. This part of the query, yeah, it is trying to find out those suppliers who have supplied some book. It's almost equivalent to a natural join. You take out the S name, you do a natural join between book and supplier, and you take out the S name. That's what it is. So this part takes out the titles of all books supplied by a particular supplier, and that must contain all the books issued by Vijay. This must contain all the books which are borrowed by Vijay. So that means the answer to this query will be those supplier names such that the title of the book supplied by that supplier must have supplied all titles, may not be the corresponding accession numbers, but if Vijay has issued 5 books, this supplier must have supplied the corresponding titles of these 5 books, at least. So if the answer to this is Narosa, then Narosa must have supplied the titles of all the books corresponding to the books issued by Vijay. If Narosa is there, East must have taken all the books corresponding to the books issued by Vijay, etc. This is equivalent to the divides relation was used in relational algebra to get this. The for all expression was used in tuple relational calculus to get this, and this is the style which we do, which we use to solve such queries in SQL. You will remember we have solved this particular example in relational algebra using the divides relation. You will also recall that we have solved this example in tuple relation calculus using the for all query. And now we are using the contains operation to solve the same problem in SQL. Other than this, there are several other features. In set, these are all set based operations. Let us see the first part. This is a valid complete SQL query. Select borrower name from user T where exists. Exists means the answer returned here is non-null. Exists means the query which is returned here is non-null. So what is this part saying? This part is saying select star. Star means all the attributes from supplier and borrow, where sub dot accession number equal to borrow dot accession number and T dot card number equal to borrow dot card and S name equal to Vijay. Okay. Supplier and borrow have got accession number as the common attribute. Okay. And T dot card number, T is this fellow. So I want the name, suppose in my whole answer name Vijay is there. Then for Vijay, Narosa has supplied some book. This will return, suppose Vijay is there in my answer, then this part will say that this will return the set of all tuples of sub cross borrow such that Narosa has supplied a book which is currently issued to Vijay. This part, if Ajay is there, then Narosa must have supplied a book corresponding to Ajay. Only then will something come up here. So this will be non-null provided for a particular name Narosa has supplied a book issued by that person. So this query exists means this is non-null. So this query means give me the name of all borrowers who have issued at least one book which is supplied by Narosa. Other than exists, you can have not exists as well. This is exists. You can have not exists. If I had not exists, then it would have been give me names of all borrowers such that they have issued no book supplied by Narosa. Not exists means if this is null, then not exists is true. If this is null, it is just the opposite of exists. We have got in, which is element of, exists means empty, not exists means not empty. And let us see what this complete one means. It's the same thing. Just I have put in allied. Instead of Narosa, I have put in allied. So this part says that this particular borrower has the list of all items which this particular borrower has borrowed from, if it is supplied by allied. This is if it is supplied by Narosa, and this will give you the name of all borrowers who have supplied at least one book by Narosa and no book by allied. We had done a similar query in relational algebra as well as tuple relational calculus, especially in relational calculus where we use the not there exists. There exists something and not there exists. This is similar to that type of a query which we did in so you've got exists, not exists, in and several other set operations. So SQL is basically a language which combines both relational algebra and relational calculus and uses some interesting operations like in, contains, all, some, exists, not exists. These are all set operations over and above the standard set operations of union, intersection, minus, and the relational algebra expressions, the rename operations, and the propagation of variables. This style is like relational calculus, whereas the other style which we used is like relational algebra. It mixes up both relational algebra and relational calculus, and that is why it is quite a favorite among users. There are other languages of which QB is totally different type. We hope to see QBE later. But SQL, as we have seen till now, provides a lot of additional constructs so that queries can be written out in a simpler fashion. There are other constructs for aggregate operations, counting, averaging, totaling, etc., and ordering operations. You can list them out in ascending order, descending order, and other, so that the output is in the order in which you want it, and it makes it much easier to write down the queries compared to if you tried it out in pure relational algebra or pure relational calculus. It also provides you mechanism for creation of tables, creation of attributes, that is the DDL is there, and other things like updation, insertion, deletion, updation, and other aspects which would be there in a practical database. So we shall see all of them in the subsequent classes.